So in today's video we are going to be solving non-homogeneous recurrence relations as in the form of this. So when solving non-homogeneous recurrence relations, you need to break it down into the particular solution and the homogeneous solution. So an would be equal to the homogeneous solution denoted by this plus the particular solution denoted by this. So then you need to solve each separately. So you need to solve the homogeneous part of it and then the particular part of it, and then afterwards you bring everything together. So let's solve the homogeneous part. So you have a n h. So this is the homogeneous part because it all depends on a and then n. So you have an minus, so we're going to bring everything to one side and equate it to 0. So an minus 2an minus 1 equals 0. So we need to write our characteristic equation, and then there's a really quick shortcut to writing the characteristic equation. So you take the lowest term with relation to n, which is n minus 1 here, and then you write that entire part as a 1, and then you multiply it by the coefficients. So you get 2, which is a negative, so minus 2, and then the next one would be, so this would be written as r0, which is 1, which I decided to omit, and then the next term would be r to the power 1, so then the power would be increasing. So you have, and then the coefficient here is 1, so you just have r to the power 1 equals 0. So then I guess we didn't have to bring it to both to one side, but then it still works. So then r would be equal to 2. So we can now write our characteristic equation from this. So we have let me just rewrite this, hn. So we have a certain alpha multiplying the roots to raised to the power of n. So this would be the solution to our homogeneous recurrence relation. But then since it's divided into two parts, the homogeneous part and the particular part, we can't input in any values, and then far to the point we do not have like any actual values to input. So then we'll now look at solving the particular part of the equation. So we have a particular n. So this is the particular part of the relation. So we could represent it by f of n. So f of n equals 3 by 2 to the n. So here there are actually two things we need to note: that this is a constant, and then there's a bit of a table, which when there's a constant, you just represent it by another constant that you'd use in the recurrence relation. And then if it's n, so if it's a constant, let's say a, you represent it by another constant, let's say a naught. If it's n, it's linear, so it would be a1 n plus a naught. If it's n squared, let me just extend this. If it's n squared, you'd have a2n squared plus a1n plus a naught, right? And if it's r to the n, you just have a multiplying r to the n. So then this is that. So I could move it somewhere else. sorry about that. Yeah, so it's here now. So because 3 is a constant, so then we just represent it by a naught, or then you could choose any constant you like. So f of n would now be equal to a naught multiplying 2 to the n, but 2 here is the root of the characteristic equation, and then the characteristic equation has a degree. Since r is 1, it has a degree of 1. So whenever you have a root and then it has a particular degree, you then have to multiply the particular solution by n to that raised to that particular degree, let's say m for instance. So then here, since the degree is 1, we'd have to multiply this by n raised to the degree of 1. So we could rewrite it as a naught n then 2 to the n. And since the particular solution must satisfy the recurrence relation we're given, then we'd have to input this particular solution into the recurrence relation. So let me just move to the next side of the screen. Yeah. So inputting this into the recurrence relation, so whenever there is an n, we then use this n, and when there's an n minus 1, we have to input an n minus 1 into the particular solution. So yeah, here we have, since it's just n, we just use our n, yeah, then 2 to the n equals, since here it's an n minus 1, we then have to input an n minus 1 in place of n. So we have 2, then a naught, then instead of an n we have n minus 1, then 2 is still raised to the exponent of n, so then we also have 2 raised to the n minus 1, yeah, plus, then the particular solution, you always maintain it as is, so we have 3 2 to the n. So then we can now simplify. So we could divide by 2 to the n. So when we divide by 2 to the n, this 2 to the n would cancel. So we have a naught n equals, since everything is multiplying, we can divide by 2 to the n. So then 2 to the n minus 1 divided by 2 to the n, you get 2 to the minus 1, which is the same as 1/2, and then that 1/2 will then cancel this 2, so then you just have this remaining. So you have, so then we can also expand that, so we have a naught n minus a naught plus, since we divided by 2 to the n, we just have 3 here. Then we could move these two to the left hand side, so then this would subtract this, giving you 0, and then you have your a naught to be equal to 3. So then we could now input that into the particular solution, so we have that to be equal to 3 and 2 to the n. So since the solution was the sum of the homogeneous parts and the sum of the particular parts, we could then, this is now a particular solution, we could then input it and we will have our homogeneous solution. So a to the n equals the homogeneous solution, which is alpha, then 2 to the n plus the particular solution, which is 3 and 2 to the n. So we weren't provided with the values, initial values, but then if you were then provided with initial values, you could then choose to input the initial values and find each individual, which is just in this case alpha, to find alpha, but then we're not given any value, so then we could stop here. So then this is our solution. So this is basically the steps you take in whenever you're solving any type of non-homogeneous recurrence relation. So then you just have to note that if your particular part is a multiple of, or it divides the characteristic equation, or it's a root of the characteristic equation, you then have to multiply what you have by n to the power of the degree of the characteristic equation. So then if this was a quadratic equation, if the characteristic equation was quadratic, then the degree would have been 2. So then we would have raised this to the power of 2. So then it's the same thing for So that's the video for today, and hope to see you in the next part of the series. Thank you.